Hello, my name is Rob Reynolds. Welcome to Mat-073. Today we're going to look at section 8.6, and the topic is solving exponential equations and logarithmic equations. And I'm going to rely heavily on some previous lessons that I've taught dealing with the definition of logarithms and, of course, three very important properties. Maybe even the change of base property, which stated the log of x base b is the log of x divided by the log of b. So many things that we've discussed previously to help us solve some equations. So equations with variables and exponents such as 3 to the x equals 5 are called exponential equations, and we're going to need logarithmic functions to undo those exponents. Just like we need addition to undo subtraction, multiplication to undo division, we'll need logs to undo exponents. So the first thing I want to talk to you about is a one-to-one property. If you have 3 to the x is equal to 3 to the 5th, then I'll say, well, if the bases are equal, if 3 equals 3, then the only way for this to be an equivalent statement is so that x would equal 5. So that's a nice property. It's a one-to-one property. So if we could get that to happen, and I think we can in this first example, by rewriting 125, you could either do a factor tree, but I'm kind of partial to upside down division, picking prime numbers like 2, 3, 5s, and 7, and just keep upside down dividing by prime numbers, 11 or 13, and so there it is, 5 cubed. So 125 can be written as a prime base of 5 cubed, and if 5 equals 5, then I know x plus 2 has to equal 3, and of course, that only happens when x equals 1. And here's how the author decided to solve. There's also a one-to-one property for logarithms. If the log of x is equal to the log of 5, then I'm not going to divide both sides by log, but it's the same principle. The log of 5 only equals a log of 5. So the only way for this to be equivalent or an equal equation is to let x equal 5. So I'll try that for this problem, but the problem is I can't write 15 as a base of 3 because, well, it's got a 3 as a factor, but I can't write. So the only thing to do to help us undo this exponent is to log both sides. So I can do anything I want to an equation as long as I do it to both sides. So I'm going to choose to log both sides. And then I'm going to use the third property, which I talked about earlier. It's right here, where I could take this exponent and dump it out front and make it n log m. Getting back here, so this becomes x log 3 equals the log of 15. And then I can divide by the log of 3. And I'll probably either leave my answer log 15 divided by log 3, or I could write it the log of 15 base 3 using my change of base, or I could find an equivalence to it by typing this into my calculator. If you go for the 2.4649, I want to caution you, make sure you put a parentheses after that 15, otherwise you'll get wrong answers. So you may want to pause the video and just make sure you can type this in and get the correct answer. So if you ever see an e in a problem, I would choose to natural log it. Let's see, we know a couple log properties. The log of 10 is equal to 1. The log of 5 base 5 is equal to 1. And the natural log of e is also a 1. And the reason why is because of the definition of logs. There's a base 10 down here, excuse me. So 10 to the first equals 10. 5 to the first equals 5. I'm doing this fishhook. If I don't write the base, there's an assumed e down here, and e to the first equals e to the first. So whenever you see an e, I wouldn't log both sides. I would choose to ln both sides, so we could probably use this property, which comes in pretty handy. So I'm going to natural log both sides. Remember, the log of 2,000 is not the same thing as the natural log of 2,000. I'm going to use the third property again and dump this out front. And then I'm going to say, well, the natural log of e is just really 1 because of what we just learned over here. The natural log of e, even though I didn't write the base, it's there. Log e base e is 1. So I get 1.32t is equal to the natural log of 2,000. And so to solve this, all I have to do is divide by 1.32. So I'll type in the natural log of 2,000 and divide by 1.32. 5.76 is what the author is going to get here. So putting everything together on one slide, we need to know the definition if you're going to be solving logarithmic equations. So again, I call this the fishhook, b to the y equals x. Start with the base, head over to the y, and then give me the x. So that's, we can change any log into an exponent. We have, this is the change of base rule, which again, if you have the log of 5 base 3, we can't type that in our calculators until we change it to a base 10. So log of 5 divided by the log of 3. And then again, these three properties are imperative for this section. So I'm going to use the definition here to undo this log and write it as an exponent. So 2 to the 4th is equal to 6x plus 5. 16 is equal to 6x plus 5. Subtracting off 5 will give me 11, and then dividing through by 6. The only thing is I want to make sure that this is not an extraneous solution. Remember, when we graph logs, we said that all logs go through the point 1, 0 unless there's a horizontal or vertical shift. But the important thing is that logs are positive. You don't want to be taking the log of a negative. So if I were to throw an 11 6-backs in there, make sure it doesn't cause me to take the log of a negative, because if you do take the log of a negative, you'll get an undefined value. So I think we're safe with 11 6, but make sure that you check. If you have two logarithmic functions, like the log of m plus the log of n, it's advantageous to go ahead and rewrite it as one single log function so we can apply the definition. For example, if you have the log of x plus the log of y, the first property says that's the log of x times the log of y. So I'll go ahead and FOIL that up, or excuse me, not FOIL, but to distribute that up. And remember, I didn't write the base, but it's an assumed 10 down here. And you may want to write it in there so you could remember when you do the fishhook, that's actually 10 to the first equals x squared plus 9x. So setting it equal to 0 and factoring, oh my gosh, we need to remember factoring. Factors of 10 that differ by 9 are 10 and 1. Signs are going to be different. The larger term is positive. So it looks like a lot of things are coming together here. And be careful, I never said that the answers can't be negative. I said you can't take the log of a negative. And so if you plug in here, that's going to take you to the log of negative 10. So I'm going to throw out the negative 10, and the only answer is 1. But don't be deceived by thinking that you can't have x to be negative answers. I've seen problems where you have things like, the original problem would be something like this. Well, if x is negative 10 now, then that would be the log of 5 minus a negative 10, and then I'm fine, because that's really the log of 5 plus 10, which is the log of 15. So here's an example where negative 10 is fine to work. Oh, and it's also an example where maybe x equaling 1 would be the extraneous solution. So, because if you were to let x be 1, that's 5. No, that'd be fine too. But 6 would be bad. So if you let x be 6, then 5 minus 6 would give you a log of a negative. So here's an example where a positive number is bad. You'd have to throw out the positive. And this negative, for this example, I just made this up, would be good. So my point is, don't throw out negative answers. Throw out answers that cause you to take the log of a negative. So just check these solutions carefully. Remember, you can't take the log of a negative. I always like to look at the graph. That reminds me that we only want positive logs of positive answers. So here it goes. The log of a minus the log of b is the log of a divided by b. And the base here is a 3 consistently, so I'll throw that 3 back in here, and I'll fishhook, which means doing the definition. So 3 squared equals 2x plus 3 divided by x minus 1. Of course, I can use my algebra skills to cross multiply to solve. I know this diagonal, which is 9 times x minus 1 should equal the yellow diagonal, 2x plus 3. So solving this gives me 9x minus 9 equals 2x plus 3. So 7x is equal to 12, and x is 12/7. And the author got the same thing. So I have 4 more examples that are, I think, similar. I like 15, 16, and 17 because they look similar, but they're very different. Let's fishhook this guy real quick and see if we can come up with something that we haven't seen yet for an example. So let's see, 16 is equal to 8x plus 24x squared. So I would probably put this in descending order. Remember, you can divide everything through by 8, which will just help reduce this. So 0 should equal 3x squared plus x minus 2. I'll factor this real quick, 3x minus 2 and x plus 1. And here x equals negative 1 and x equals 2/3. I wanted to show you this example because you might think that negative 1 is going to be an extraneous solution. I have to throw it out, but actually I think it checks. So I think that negative 1, if you throw that back in here, I don't think that causes the log of a negative number. I get negative 8 plus 24, and that's going to be positive. So here's a case where I get 2 solutions, 2/3 and negative 1, and they both check. So here we go, 15, 16, and 17, 3 more problems, and they look similar, but they're very, very different. This is a minus sign, so it's a quotient rule. So I'll divide 2x plus 5 over x is equal to the log. Now this is a 1-to-1 property, so the log of this equals the log of that when this yellow equals this pink. So all I have to do is set this equal to that, because that's the only time that the log of the left will equal the log of the right. So multiplying, 3x equals 2x plus 5, and it's very simple. By subtracting off 2x, I get x equals 5, which does not cause any extraneous solutions. So I would say 5 is a great solution. Now look at number 15. I'm going to change it just slightly by taking the word log off of the right side, but it drastically changes the outcome of the answer. Because this time I can't use my 1-to-1 property. I have to use, oh yeah, this is a base 10, even though I didn't write it, and I'm going to use the definition by fishhooking this to be 10 cubed equals 2x plus 5 over x. And again, I will cross multiply. That's 1,000 x is equal to 2x plus 5. So subtracting off 2x and dividing, I get a very different answer. And then over here, for number 17, I've changed this minus into a plus, which means now instead of a quotient, I have a product. So I'm going to multiply this together. The log of 2x squared plus 5x will equal the log of 3. But I can still use my 1-to-1 rule. The log of this equals the log of that when, when yellow equals pink. So it's kind of like unlogging both sides. Just like you have the power to log both sides of an equation, you can also drop the log from both sides. I'm going to set it equal to 0. I'm going to find factors again, which I know is not your favorite topic, but just keep guessing and checking and make sure you foil this back together before to check this. So here I get x equals 1/2 and x equals -3, and then I want to check that -3. I don't think I can accept the -3 because that's the log of -3, so that would be an extraneous solution. So the only solution here is 1/2. Sometimes it's denoted extraneous solutions by putting it in parentheses. Honestly, at this stage of the game, I would just not even list it as a solution and just stick with the 1/2. You're supposed to try. Good luck drawing those solution set forms. I have a difficult time drawing them myself, so I would just say x equals 1/2 and call that good. If you have any questions, feel free to email me.